we're looking at trigonometry, and I will argue that it is one of the underpinning concepts of civilization itself.
That's a big call, John.
It's a big call. It just seems like some obscure mathematical stuff when you first learn it, but it's really important, and we'll go through why.
Fascinating. Yeah.
To understand this, you'll need to know about fractions, Pythagoras' theorem, basic algebra, the Cartesian plane for the latter part we're looking at, angles and degrees. We'll basically mention radians, and the fact that the angles of a triangle add up to the angles of a straight line, so 180 degrees. You okay with all of that?
Yep. Sounds good. Exciting.
Yeah, it is actually. So, literally triangle measuring, trigonometry, and once you can measure a triangle, you can measure straight-sided figures. Here's some random straight-sided figure. You can always divide it into triangles. You can divide any triangle into right-angled triangles. So once you can measure things in a right-angled triangle, you can measure straight-sided figures.
So trigonometry literally it means triangle measuring.
Yeah.
So trigonometry is about measuring triangles.
Trigon, triangle.
I never got that.
Oh,
so that's really good. Thank you.
It's about measuring a specific thing about triangles.
Yeah.
Important in one way or another to just about all of the ancient civilizations. And all of these things. The first one we actually looked at that tablet when we looked at the Pythagoras' theorem, but it was really the ancient people in Mesopotamia looking at sets of numbers that will create a right angle for you. So the Egyptians looked at the Chinese. Really important, and the reason it's important for, or the reasons this is important for civilization is you need it or something like it in order to navigate by the stars. And if you can't navigate by the stars, you can't trade overseas very well because you can't work out where you are. You can't even travel into unknown areas. So
it's kind of the lifeblood of the whole thing, isn't it?
So once you start, so civilization is really, you're talking about having a lot of people live together, literally people living in cities, and that's what's hard without this. It's hard to navigate without this, hard to measure time, distance and direction if you can't do it by the stars. It's hard to do major construction. Unless you can sort of measure the angles at the bottom, but what's the angle at the top going to be like? That sort of thing. What's the distance at the top if we start there? It's hard to measure land. So if you're living by the Nile River and the markets get flooded out every year and you have to recalculate who owns what land.
Right.
If you're a small group, you kind of know, but if you're a big group, it actually becomes really important to establish land ownership and to be able to agree about who owns what, or you're just going to fight the whole time. And more recently, for reasons we'll come to see, sorry, I went too fast there. For reasons we'll come to see, if you're looking at anything with a wavelength, or with a waveform, which is electronics, radio waves, any recurring phenomenon, that also uses trigonometry.
Oh, is that right?
Yeah, so we don't have this. It's actually would be really hard to live in the modern world, but it would be really hard to have more than about 200 people, which is about the number of people you can actually know.
Yeah.
It'd be hard to have them living in the same place without fighting. And so this is kind of a really fundamental idea.
Right. It is fundamental to civilization, isn't it?
So when we looked at Pythagoras' theorem, we saw that the ancient Egyptians could tie knots in a rope and form a right angle. That's how they could do the sides 3, 4 and 5. And what that means is if you know that something has two sides, 3 and 4, you'll be able to tell that unknown side is 5. So once you have a right angle, you've got two sides. You can use Pythagoras' theorem to work out the third side.
Yep, I remember
Similarly, we can work out that way. In terms of the angle of that 3, 4 and 5, it happens to be approximately equal to 36.87 degrees. And so once you know that angle's 36.87 degrees, and you know that the bottom part is 4 units across, whatever a unit is, you ought to be able to work out the height or the length of both the other sides, where we get into triangle measuring. Because it's fixed. Like if one of the sides changes, it's going to change the angle there. It's not going to equal 36.87 degrees anymore. It is fixed, but the question is, how do you work it out? it's fixed. Yeah, if you have a small triangle, that is not going to change. It's still going to be 4 by 5. It doesn't. We don't care how long each of those units is. Could be.
Yeah. Okay. Could
be a light years. Yeah. Could be anything.
Bring in light years again.
It's not going to change. So supposing we kind of go, well, let's make that 10 units. Well, that's actually just 5 lots of 2 units. So you can still think about it that it's 5. So it's still going to be 6 and 8. It's 4 lots of 2 units along the bottom and 3 lots of 2 units.
It keeps the same.
So it keeps the same dimension. So we can think about this as a fraction. So if we look at the opposite side compared to that hypotenuse, the long one there, it's going to be 3 on 5, which is the same as 6 on 10. So the fraction isn't changing is the key thing, the value of the fraction, even though the numbers change, because that ratio is going to stay the same.
Yeah.
So it's the same thing as when you multiply the numerator and denominator of a fraction, the value of the fraction itself doesn't change. Similarly, the bottom line across the hypotenuse is going to be 4/5, which is the same as 8 on 10, and the side opposite compared to the side closest is going to be 3/4 or 6 on 8, same thing. So it ought to be possible to work out from that what the other lengths are, but the question is how you do it, and we need some consistent terminology here. So we'll call the angle there theta, which is, we won't use x because we use x for something else later, but just some angle. Using the Greek letter theta is commonly used for that. Could use anything at all. But
so theta is used for an unknown angle.
An unknown
just
angle.
An angle.
Yeah, right. just an unknown angle.
Yeah.
And we'll call the green. So we saw this when we looked at Pythagoras' theorem, the hypotenuse.
I met hypotenuse in primary school from vague memory.
Probably.
Right?
Literally stretched under. So stretched under the right angle. The one that's adjacent to it, not surprisingly, it gets called the adjacent angle, the adjacent side.
Yep.
And the one that's opposite is even easier because it's called the opposite.
Right.
And so if we were to say, all right, that angle's theta is 40 degrees, the adjacent is 10 units instead of, you go, okay, so with that changed angle on that, what is the opposite and what is the hypotenuse? They can only be one thing. They can't change, but what are they? How do we work out? Is the big question of trigonometry.
Okay. So if you were building a pyramid, seeing as it's triangles, then you could use this to work out if you wanted the pyramid to be a certain height.
That's right.
This would help you map it out on the ground and build it.
Exactly once. If you knew what angle you were, exactly right, what angle you were elevating and how far you were drawing on the ground, you could then go, okay, that's going to wind up being this high, so it's going to wind up being that long, that angle. If you're navigating, you go, if we move that far and with that angle, then that's going to be that far away. That's the sort of thing that opens up to you. You can't do unless you can measure it. And so the thing is, we could make that 3 units. Or we could make it 20 units. The key thing is that those sides will change in length, but the ratios between them won't change. Okay. That's the key thing. That's the useful bit. The ratios are going to be consistent, and that's the fact that makes what we're going to look at doable. So getting back to giving things names, we call the opposite over the hypotenuse, for reasons historical, the sine, the adjacent over the hypotenuse, the cosine, and the opposite over the adjacent, the tangent. There's not much in maths that you want to memorise. That is actually useful to memorise. So there's a useful way, little mnemonic to memorise it. SOHCAHTOA, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent.
It's funny because I remember fiddling around with trig tables, but I never remembered them being related to triangles. So it's really helpful to know where they come from. It makes a lot more sense now.
There you go. So just in order to do this calculation, to work out the length of the opposite sides using that. So we could look up on our trigonometry tables, or in my case on the calculator, same thing, the cosine of 40 degrees. That's going to give us that ratio of the adjacent over the hypotenuse. which in this case is going to be 10 over the hypotenuse, and you look at the cosine, it's 0.766, and it's going to be that. Once you have the angle, that's the cosine. It's not going to change once you know the angle. That's the key bit. So just some mathematics, we flip those upside down, taking the reciprocal of each side, multiply both sides by 10, do the calculation. We can go, the hypotenuse is 13.05, etc., etc. So we now have worked out the length of that hypotenuse.
Yeah,
or
very cool.
at least close enough to be useful. Even easier with the opposite. The tangent of 40 degrees is 0.83, etc. So the opposite over 10, the opposite over the adjacent is going to be opposite over 10. Yeah, I just said that. Multiply both sides by 10. That's the length of the opposite.
So they really use this a lot in space travel.
You use it a lot in absolutely anything.
Everything. I see your
use
point
it,
now, yeah.
Still use it in building.
Yep.
Use it for everything. There's a few other things, and this is where these are things you wouldn't try to memorise, just letting you know they're there. If you want the reciprocal of those, they're called the cosecant, the second, which is really confusing. Sine is cosecant, cosine is second. Don't know why they did it that way. And tangent's cotangent. Like I say, don't try to remember that. It's here if you need it. And if you need the inverse, which is a more useful concept. So we know what the sides are. How do we work out the angle? Again, simple rate. Use those. And again, if you're using tables, you just if you're using a calculator, you just put in arc
I just
sine.
realised I showed my age by saying tables.
Yeah, that's right. Well, you did, but it's useful to know that that's the way it used to be done, and the only way it could be done.
Sure.
So that's so far so good. The only problem with this is you're limited to angles of less than 90 degrees because that stops being meaningful. So once René Descartes came up with the Cartesian plane, people came up with a new way of defining things. It doesn't help you find it more easily, but a new way of defining these angles that lets you think about angles more than 90 degrees, which works like this. Uses a thing called the unit circle. It's a circle of one radius in diameter. And if we have an angle theta there, the radius will go out there. So, and in a unit circle, that's going to be, the radius is going to equal 1, which is why they call it a unit circle. That'll hit that circle at some point xy. Now, the height of that's going to be y. And so the sine of the angle is going to be y over 1, or just y.
Okay.
That making sense?
Yeah. Yep.
Similarly, the distance across there is going to be x, so the cosine of the angle is going to be x over 1, or just x. The tangent of the angle is going to be y over x. And so once you know that, you can use that definition to then look at, well, now we know what the cosine is there. It's going to be negative, but it's still going to be the x value
because of the circle.
Because of the circle.
Yeah,
so we can have they'll both be negative.
You can
there.
put them anywhere you like.
We still have a definition. In fact, you can keep going round the circle. You can have an angle of more than 360 degrees. It'll just work that way.
And this is Descartes as well?
No, this happened. Well, he might have come up with this actually. I'm not actually sure who came up with this, but it wouldn't have been terribly far from that time because it just suddenly opened up so many ideas.
Yeah, right.
And one of the key things that we're going to change what we're graphing now. We'll keep that graph there. Put this on white now so you can see that we're graphing something different. It takes a moment to get your head around this, but once you do, it's not too bad. What we're graphing here along the horizontal axis, we're not calling that y, we're calling that theta. So that's going to be what we're graphing against is the size of the angle, but we're keeping the same sine value, which is the y.
Okay.
And look at what that looks like. So that when we first start out the angle just there, it goes up like that, and then the sine value goes up like that, and it starts to tail off when we get to the top. When the angles now hit 90 degrees or pi on 2 radians, the sine is going to equal 1. The y value is going to equal 1. And then the y value starts to fall away again. So when we're at 180 degrees, the sine's equal to 0, the y value is 0, and then we go negative like that. And so what you end up drawing is this sinuous, and that's where the word comes from, sinuous wave, and then you can keep going, and so you draw a wave that looks like that.
Wow. So that can visualises as a wave.
That you can visualize it as a wave. If we looked at it like that, if we visualize sine like that, we visualize cosine like that. It also forms one of those waves. It's just we just call it being out of phase with the other. And with suitable manipulation, you can then use x and y to describe any waveform. The waveform won't necessarily have that, might have the shape, it might be spiked or square or whatever, but that's just mathematically using sine and cosine. So therefore, once you have those two concepts, you then have a mathematical way of describing waves, which then lets you get into electronic engineering and all sorts of other things, allowing
certainly the foundation of civilization, John.
Certainly as we know it. Yep. Thank you for watching.